In this video, we are going to discuss the small scale fading parameters. We know there are two kind of fading techniques are there. One is a small scale and another one is a large scale. So as its name implies, small scale fading encounters for a small distance, whereas the large scale fading encounter for a longer distance. And this small scale fading have a fluctuations. Rapid fluctuations are existing in case of a small scale fading. So we look at the parameters which describes the small scale fading effects. So fading is phenomena that occurs due to the varying parameters and conditions of the channel during the wireless propagation. So as I said, this dotted blue line indicates the large scale fading which encounters over a longer distance, and there is a little fluctuation in this case, whereas a small scale fading occurs during a shorter durations which have a rapid fluctuation. So small scale fading refers to the rapid changes of the amplitude and phase over a short period of time and short distance. And the small scale fading depends on the nature of the transmitted signal with respect to the characteristics of the channel. There are various factors that influences the small scale fading. First one is the multipath propagation. So we know multipath propagation is nothing but the wave takes a multiple path like this before it reaches the receiver in a wireless communication. So due to the various phenomena like diffraction, reflection and scattering. So all these will be collected together and the effect will be calculated at your receiver side, and which causes the signal at the receiver to be fade or a distorted one. And the second phenomena is speed of a mobile receiver, that is the relative motion between a transmitter and receiver results in a random frequency modulation, which is due to the different Doppler shift, because both transmitter and receiver are traveling in a different speed, isn't it? That speed also affects the signal. So Doppler shift may be a positive or a negative, depends on whether the transmitter and receivers are moving together or moving away from each other. And third factor is the speed of the surrounding objects. If the speed of the surrounding object is greater than the mobile, then the fading is dominated by those objects. If the surrounding objects are slower than the mobile, then their effect may be ignored. So you just imagine while you are traveling in a train, you look at the surroundings. You find those surroundings also travel at the same speed as we travel in a train, isn't it? So that will influence the fading effect. And the fourth parameter is the transmission bandwidth. We very well know if a signal bandwidth is, there is a relation between the signal bandwidth and the coherence bandwidth of the channel. If your signal bandwidth is less than the channel bandwidth, then your signal can easily travel inside a channel. Whereas if the signal bandwidth is larger than the channel bandwidth, it's very difficult to transmit the signal inside a channel, isn't it? So if the signal bandwidth is greater than the coherence bandwidth, it creates a distortion. If the signal bandwidth is smaller than the coherence bandwidth, it creates the small scale fading. So these are the four factors which affects the small scale fading. So there are various methods to measure the small scale multipath effect, that is direct RF pulse system, spectrum sliding correlator channel sounding and frequency domain channel sounding. These techniques are also called as the channel sounding techniques. So this is the very important for small scale fading calculations. So in case of a direct RF pulse system, main objective is to find the impulse response. So a narrow pulse is used for a channel sounding. At the receiver side, the signal is amplified and detected using an envelope detector. It is then stored on a high-speed digital oscilloscope. If the receiver is set on averaging mode, the local average power delay profile is obtained. So this is the setup used to measure the direct RF pulse system, where we are using a pulse as a reference and we are transmitting in a receiver link, and we calculated using the predefined formulas. And the next important parameters associated with this small scale parameter is the delay spread and coherence bandwidth. So RMS delay spread is nothing but describes the time dispersive nature of the channel in a local area. How your channel is dispersed based on a time. So a received signal suffers spreading in time compared to the transmitted signal. So this delay spread can range from a few hundred nanoseconds for an indoor scenario up to some microseconds in case of an urban areas. And the next parameter is called as the maximum excess delay. Suppose you consider it is to be of x dB, then it is defined as the time delay value after which the multipath energy falls to x dB below the maximum multipath energy. It is called as the excess delay spread. And the coherence bandwidth is denoted as B suffix C, which translates time dispersion into the language of frequency domain. It simply specifies the frequency range over which the channel affects the signal spectrum. Okay. Next one is the coherence bandwidth. So another definition of this coherence bandwidth is range of frequencies over which the channel is considered to be a flat. Flat in the sense the channel passes all the spectral components with equal gain and linear phase. And this is a definition that depends on a RMS delay spread. So these are the formulas to calculate the mean excess delay and RMS delay spread, which is calculated by means of a first moment of the power delay profile and square root of the second central moment of the power delay profile. And next we move on to the Doppler spread and coherence time. So this Doppler delay spread and coherence bandwidth describe the time dispersive nature of the channel. They don't offer any information about the time varying nature of the channel. Whereas this Doppler spread and coherence time are the parameters that describe the time varying nature of the channel in a small scale region. Okay. So the Doppler spread, which is the measure of spectral broadening caused due to the motion. So in order to compute to the Doppler spread, we consider the FD, Doppler shift, okay, frequency. So Doppler spread BD is defined as the maximum Doppler shift, that is FM, which is equal to V by lambda. V is the velocity in which we are traveling. Lambda is your operating wavelength. If transmitted signal bandwidth is large, so that Bs is much greater than this Bd, then effects the Doppler spread are not important. So Doppler spread is only important for the low data rate applications, that is only for a slow fading channels. And coherence time is nothing but the time duration over which the channel impulse response is essentially invariant. Okay, so the coherence time is defined to be Tc is almost equivalent to 1 by Fm. If the symbol period of the baseband signal is greater than the coherence time, then the signal will distort. Since channel will change during the transmission of a signal. And coherence time is defined to be Tc is equivalent to 0.423 by Fm. So coherence time definition implies that two signals arriving with a time separation which is greater than the coherence time Tc are affected differently by the channel. That's what the conclusion we could get from this coherence time. So these are the small scale fading parameters. Kindly take down these assessments for a better understanding. Thank you.